In the present video, we're going to introduce the matrix menu in wxMaxima. Part 1, because we are going to have to split it. There's so many things to present there. We're going to have to split it in several parts. So let's get started by looking at this particular document in Maxima. I have the examples presented in the order in which the commands appear in the matrix menu. And so the first one is called generate matrix. And this one is basically used to represent a matrix with elements with subindices. And so, for example, if you put A lowercase there and name the matrix A, and you say OK, you're going to produce this command called generate matrix. And that's going to give you, in this case, I selected the 3 by 3. Most of the examples will be 3 by 3 here because we don't want to spend a whole lot of time in them. You can experience with larger matrices on your own. So this command then generates this instruction gen matrix A 3 by 3 that produces this matrix. Now suppose that we want to generate element b sub ij equal to a certain function of ij. Here's an example. You use the matrix generate matrix from expression menu. Instruction here. Write a function of ij as I did here, 10 over I plus j. Again, using 3 rows for 3 columns, and I call in the matrix B, and that gets me this result. Now, you're just gonna get this result. We're gonna store B. Matrix B then has this expression, and it gets stored in matrix B. The function that generates the elements is called lambda. Okay. You can enter the matrix by yourself. You go matrix, enter matrix, which is going to ask you how many rows, how many columns, what name you're going to give it. So I give the name C. It's a type general. It could be diagonal, symmetric, anti-symmetric. And then you get this form where you enter the numbers. You can press tab to go from one element to the next one. Once you have entered all the numbers in there, and you press OK, and you get something like this, which I'm entering this matrix C, which is the generic matrix. If you select entering a symmetric matrix and say 3 by 3, you only get, of course, the top triangular part of the matrix, so you can fill up with numbers, and it will produce for you the symmetry that you requested. Nested list to matrix. A nested list is just a series of lists of the same size, separated by commas, and so everything you type in between brackets is a list. So this is a list of lists. I'm going to type the list of lists, enter it, so it becomes active in the memory, and then when you do the matrix nested list to matrix, it produces this command, which converts these lists into the rows of a matrix. And I'm saving this result into matrix E. The next two commands deal with importing from CSV files, and I'm going to skip those. Then you have invert matrix. This is the inverse matrix, and when you activate this command, then you get the invert command. And so here I have the inversion of matrices B, C, and D. We could try, for example, here invert matrix A. And that gives you this huge result. It's a 3 by 3 matrix. And so this will be the elements of the inverse matrix of that generic symbolic matrix. Here's another example, a simple example with a 2 by 2 matrix. Okay. In linear algebra, there is what is called the eigenvalue problem, and it's written this way. Square matrix A multiplied by vector X equal to a number lambda multiplied by X. The values of lambda are called the eigenvalues, and the corresponding values of X are called the eigenvectors. This equation can be written like this equation in terms of the identity matrix and the eigenvalues lambda, and make it equal to 0. The only way that this equation has a non-trivial solution, then the trivial solution would be X equals 0. For it to have non-trivial solution, the determinant of this must be a singular matrix. So the determinant of this matrix must be equal to 0. When you expand this determinant and make it equal to 0, you generate what is called the characteristic polynomial of the problem. And so Maxima has this option is called characteristic polynomial, where you enter the name of the matrix and a variable to represent the variable to be solved for. And I did here for matrix E, which is one of the last matrices that I enter, and it gives me this command that says expand char poly, and it gives me this polynomial. If I use equations roots of polynomial, I get the command all roots that will give me the eigenvalues. It turns out that this is a real one, and there's a couple of complex conjugates. Now we're going to apply it to matrix E. Now this is a long result using complex numbers, but not in a simplified way. You get two lists, this one that starts here and ends right here. Is the list of the eigenvalues. This is one eigenvalue that ends up in this comma, second one and third one. And here it tells you that each one is repeated only once. This second list here is the multiplicity of the results. They're repeated only once. Suppose that I want to convert this to something I can read, and you can use the floating point. But it's still giving me a complex way to represent those complex numbers. And so what you can do is go to simplify, complex simplification, convert to rectangular form. Just give you this command, and now the numbers look a little bit better. Now they still have a lot of digits in them, and you can reduce that, but let me summarize here the three commands that we use. Eigenvalues E. Now the dollar sign here actually separates one command from another, but when you use the dollar sign, there's no output to that command, and so there will be no output for the first two, only for the last one, and that's basically what you want. And so I recommend using this collection of commands to find your eigenvalues. And then the other thing I was going to say is change the precision, so you only need 6 digits. Go to numeric, set display precision, change that to 6. It gives you this result. And then when you repeat the results before, you only get 6 digits, and it's easier to read. Symmetric matrices such as matrix D will produce real eigenvalues. Now we say, well, they don't look very real to me, because you get 10 to the minus 16i. So there's an imaginary part. This is numerical errors, because these two numbers are very small. The 10 to the minus 16, they're basically 0. So another thing you can do here is get the real part of the last result, and you drop those imaginary negligible parts. And so you get your 3 eigenvalues. Now this is a list with 2 lists inside. How are we going to get rid of that? First, store the list in L1, and then you can refer to the elements L bracket 1, L bracket 2. This will give you the 2 elements of L1. And then you can use the sequence of index to extract from L11 the eigenvalues.